All right, well, we might go ahead and get started. I see people still trickling in, so that's fine. Thank you for joining the Analogues Focus Group. I just wanted to say I'm Jen Hildman. I'm with NASA Ames Research Center, and I wanted to thank our sponsor for this focus group, NASA SSERVI, the Solar System Exploration Research Virtual Institute. And so SSERVI has been sponsoring this focus group, recording these sessions, and this talk will be posted online on the SSERVI Analogues Focus Group website after this presentation. So for folks who couldn't make it in person, we're glad that you're joining later and watching the recording after the fact. We're very pleased to have Jim Head speaking to us for today's seminar. I'd like to embarrass Jim a little bit because I figure if with every seminar Jim gives, if we learn a little bit more about his illustrious career, we'll start to understand all the contributions he's made to the field. So Jim started his career, he earned a BS, we're going to go way back, from Washington and Lee University in 1964, and he got his PhD from Brown University in 1969. He then spent 4 years with Bellcom in Washington, D.C., in the NASA Systems Analysis Branch. And from there, his research focused into lunar science in the Apollo exploration program, where he not only trained astronauts, but actually worked the Apollo program during surface operations from a science perspective. Following this, he was the interim director of the Houston Lunar Science Institute. And then he joined Brown's Department of Earth, Environmental, and Planetary Sciences as an assistant professor in 1973. He was promoted to full professor in 1980. He was named to the James Manning Chair in 1990. And in 1995, he was named to the Lewis and Elizabeth Shirk Professorship in Geological Sciences. So Jim's career has spanned the gamut of planetary bodies, robotic exploration, human exploration, and so we're very thrilled that he's able to come and talk to us today. And so his presentation will be focused on Antarctic fieldwork. Jim has been to the depths of the oceans, to the poles of the Earth. And so we're going to learn about how some of this fieldwork provides lessons learned for human exploration of the moon and Mars. So Jim, I can turn it over to you.
Okay, thank you very much, Jen. It's a pleasure to be here, and I really enjoy these discussions because the intertwining of all the research we do at NASA and in our academic careers, et cetera, with our great students and so on, is all linked to basic exploration. Science is exploration. It's as simple as that. So I want to start by saying that uh, talking a little bit about different types of planetary analogs. Analogs are the key here. The first one is planetary analog field work for research, okay? So this is literally trying to understand how things work and then applying them to the planets, et cetera. We could do volcanology, we can do, the picture on the right is a picture my colleague took of me in Antarctica. That is not a snot sickle or a cigarette. It's just basically an icicle off my mustache there. It's really cold, it's a different environment, but it has great implications for Mars. The second type is really planetary analogs for astronaut training. So when we're training the astronauts, there's a really critical set of ideas and rules that need to apply, and I'll try to outline some of these. We'll use Apollo 15 as an example in a little while. And the key thing you want to do here is not like, okay, you got to learn a basalt from an anorthosite. That's basic too, but you really want to teach problem solving because that's what they're going to do on the moon and Mars. And it's really important to take that approach when we do astronaut training, much as Dean Epler and colleagues did in post-Apollo Desert Rats, and it's the same kind of thing Lee Silver and the group of us, USGS, et cetera, did during Apollo. And then, of course, it evolves in terms of site-specific activities. So astronaut training, once a site is selected, you end up focusing on analogs that are more like that landing site. And then, of course, you use them towards the launch to do mission simulations. You actually go out in the field. We would have a tent as like a mission control. One of us would be the Capcom. The astronauts would be in the field. And it would be a real simulation, a mapping exercise, a simulation, et cetera. And it has to be an analog that's really kind of important. The third type, of course, is for specific landing sites for the moon and Mars. And this means thinking ahead. And this is really kind of interesting because we're in new territory here when we're dealing with Artemis onto the moon and onto Mars. And so, essentially, we're going to be thinking about things, particularly in the South Circumpolar Zone, which are very different. They're much more like Apollo 16 than they are like virtually all the other sites we went to. And then as we think about Mars, it's the Wild West out there, okay? There's so many different analogs. Where are we going to go? What are we going to do? That's going to be really interesting for the training as well. And we need to include that as we think to the future. So just three different types here is an important way to think about it. Now, last time in October, uh, I dealt with the themes that are listed in yellow here. What is field work? The definition, the importance of planetary analog field work, dangers of planetary analog field work, the equifinality issue, the whole point that, just because it looks like a duck and quacks like a duck doesn't mean it actually is a duck, and you need to really figure out, how you prove these kind of analogs. And also, a key point there is, and I'll bring this up a couple of times, is that planetary analogs have a bad name because people say, well, what can you do? I mean, look at Antarctica. I mean, yeah, okay, Mars. It's not Mars. It's not a CO2 atmosphere. It's not 6 millibars. And the answer to that question is you learn how the processes work. Nobody is dumb enough to say, oh, I'm on Mars. I mean, first thing you realize is you can breathe, and that's not Mars, okay? So that's a really critical item too. It's really important to think about the goals of planetary analog field work. I tried to list the three here. What are we trying to do here with these analogs, et cetera? Which of those three does it fit in, and how do we go from here? And then there's some examples of analog field work we talked about as well. So I want to just briefly review that, for those of you who missed it and haven't had time to take a look at it. So we looked at basic examples of planetary analog field work and lessons learned. Active eruptions in Hawaii East Rift Zone. These are all things that I've been involved in my field work over my course of my career so far. And they're kind of personal experiences, but Mount St. Helens eruption, Manicouagan, Pacific Ocean seafloor processes, Arctic Svalbard, and we were just beginning to talk about the Antarctic McMurdo Dry Valleys and their implications there. And what we did for each one, I'll use the Ocean Floor Exploration Reference Mission, is to think about a reference mission. What do we learn from this? First of all, the goals. Why, what, when, and where? What's the question? What are we trying to do here? And then how do we get there? Okay, well, sometimes it's easy. Sometimes it's not so easy. Getting to the bottom of the ocean is not so easy. What kind of support do we need? Okay, we need a research ship, a deep sea submersible, and a huge infrastructure. Okay, logistical support. When you go to the bottom of the ocean, you kind of want to be able to have a backup. Kind of, and support, rescue, repairs, etc. And then what do we do and how? Scientific dives, traverse sampling, observations. What's the relative role of human and robotic exploration? When in seafloor exploration, while we're down on the bottom of the ocean, the other half of the science crew is sleeping so that at night they can get up and tow a module of instruments that actually gets broader context for the site. So human and robotic exploration, you have to think about those relationships. What are the relative roles? And then, of course, the most important thing is, what is the legacy? What did we learn? You just don't go and do things for fun. What did we learn? So we talked then as one of the examples about diving on Seamount 6 off the East Pacific Rise and south of Mexico. And then, of course, the Loihi Seamount that is coming up just southeast of Kilauea in Hawaii. And of course, here's the research vessel. Okay, you get lowered over to the side, you sink to the bottom of the ocean for, it takes about an hour and 20 minutes to get to the bottom of the ocean, and then you do your work for a day, and you come back up at the end of the day. And the key here is that we learn a lot. Okay, what's the, in fact, legacy? It is, in fact, scientific results. So we find out how volcanic eruptions work at depth, and then we apply this to the Venus high-pressure environment. So we have some papers on that, and that's the scientific legacy, the making a contribution from the exploration. And again, we'll touch base again on the Antarctic Dry Valleys. Okay, so let's pick up there where we left off last time, and think about why we want to go to the Antarctic Dry Valleys. One of the key points here is, if we look at this plot of mean annual temperature, okay, here's 0C, and mean annual precipitation in millimeters, okay, you can see this is, check the scale out here. We can divide the Earth's environments up into arid, semi-arid, selva, humid, temperate, periglacial, and glacial. And the key here is we really want to get to situations in which we can have more essentially Mars-like environments. So we're all raised in the mid-latitudes, and we all think about things in terms of temperate climates, et cetera. But we get to go to Antarctica to study how these concentrated environments work. You can see here only a small percentage of Antarctica is not covered with ice. That's the dry valleys you're looking at here, and you're tuning in right to our field area, right in this area here. That's Don Juan Pond, the most hypersaline body of water on the Earth, and this is one of our field areas that we spend a lot of time. We'll come back to that in a few minutes here. But the key here is that we actually can study this kind of environment, and we end up in this. Here is again the Don Juan Pond area here, okay? And you can see this is one of our field areas, the upper right valley, and this one here is Beacon Valley, which is quite distinctly colder, believe it or not. And then we can go down towards the coast to look at other environments as well. And the thing about the Antarctic dry valleys that's so incredibly important is not only is it cold, okay, is it very cold, okay, minus 20 C mean annual temperature, but it has variations and in altitude. You can see here that translate into variations in temperature and mean annual temperature. So we have a stable upland zone that we look at in Beacon Valley here, and essentially there is no melting there. It's only tiny bits of melting that are related to heating up of rocks. On the other hand, when we go to the coastal thaw zone, there are parts of the year when the mean annual temperature, when the peak seasonal temperature is above freezing, and you get, in fact, meltwater and cryoturbation activity. And then the inland mix zone has a little bit of each, and that's why we spend a lot of time there. We can study what Mars might have been like, is like today, and we can study what Mars might have been like early on in its history by studying the Taylor Valley and down towards the coast. So this is really great. It's not only a laboratory for the study, but within it, it has analogs to a lot of different things. And you can see here, if we put in that same diagram I was just showing you of mean annual temperature versus mean annual precipitation, you can see, in fact, that the Antarctic dry valleys fit in this glacial area here. And the stable upland zone is down here, and the more active zone is up here. So we see variations within the glacial environment. And these are very analogous to what we see on past Mars and Mars today. Okay, so this is really critical. This is really important. We're in the place where we can really learn something. And when we look at these three zones, the stable upland zone, the coastal thaw zone, and the intermediate zone here, the mix zone, in the mix zone, we see, in fact, what the mean annual temperature does. Here we can see temperatures as a function of time, and we can see the effect that has, as I talked about a little bit last time, on basic landforms, which are like polygons. Okay, we have ice-covered polygons, we have sand wedge polygons, we have ice wedge polygons. All these things we can see and look at, and actually, as Joe Levy and others have done from the field work we've had, to actually provide paradigms for the interpretation of these on Mars based on really, really solid analogs. So this is one of the reasons why this is so important. It's really, really critical. And the other thing is that in the Antarctic dry valleys, the glaciers are cold base. It's so cold that the glaciers are coming out over permafrost, and therefore they are not wet based, which is like they have lubricated liquid water at their base, and they slide over those, making all kinds of interactions and erosion and et cetera, and drumlins and eskers and things like that. But they're literally welded to the subsurface. They're welded to the substrate. And we get debris-covered glaciers like these. We get alpine glaciers like these. And so the dry valleys provide a huge range of opportunities here. You know, I've spent a whole season in this area up here, traversing this whole thing, making measurements on ice thickness, making measurements, ground penetrating radar, digging trenches, et cetera, to characterize this debris-covered coal-based glacier, which has really been helpful in interpreting Mars. So both Antarctica and Mars are currently extremely cold, hyper-arid deserts, okay? Very dry, et cetera. So this really gives us the opportunity to use the information we get from these analog studies, which, many, many papers on these, okay, by our group, by other groups, the group at NASA Ames, Chris, others, lots of really important contributions from Antarctic field work. So how do we apply this? What's an example of how we would apply this to understanding Mars? Well, here's a very simple description, if you will, diagrammatic representation of Mars climate history and the climate system. So we start with the Milwaukee, I think most of you are familiar with the Milwaukee, Hesperian, and Amazonian. I'll assume you are. The earliest period, the intermediate period, and the longest period, the Amazonian. And we know from a variety of pieces of evidence that the Amazonian was extremely cold and arid. It's about 213 Kelvin mean annual temperature today. We know that Hesperian was transitional between these two, and the geological evidence strongly suggests that it was warm and wet, okay, in the earliest history of the Noachian, valley networks, other types of things. And of course, this is borne out in many ways by essentially the mineralogical evidence. Jean-Pierre Bibring, Christensen, Murchie et al., Mustard et al., done really incredibly important work that's revolutionized the way we look at Mars. And they have shown that there are clays in the essentially Noachian, which suggest liquid water and warm conditions to produce alteration of surface rocks. And then, of course, the anhydrous ferric oxides characterize extremely cold and arid climate. That's another thing we've been able to contribute to in looking at these comparisons. And then, of course, we have this transitional period, which is a bit of a mystery because sulfates dominate there. What's that all about? Well, let's just go with the extremely cold and arid and the warm and wet and see if we can understand and test these ideas. And what we'll do is we'll use this Noachian climate history diagram here as a frame of reference, okay? So if you look at the temperature in Kelvin from 210 to 300, the current Earth temperature is about, these are mean annual temperatures, about 289 K. That's up here. Of course, the melting point of water is 273 K. Here's a Noachian down here, early, middle, and late, going into the Hesperian. It's a span of about 400 million years. And the current Mars temperature is really cold, okay? It's 213 K, okay? So where are we here? Are we up here in the early part of Mars history, or are we elsewhere? More like the Amazonian, which is right here today. So let's use this as an example and see what the geological evidence tells us. The geological perspective, which has been beautifully documented by Helen Howard, Craddock, Irwin, Moore, Andrews Hanna, and others, really strongly suggests on the basis of crater degradation, history, essentially valley networks, open and closed basin lakes, etc., that the hydrological system was vertically integrated. That is, the temperatures were so high up here in the warm and wet range, okay, mean annual temperatures, that in fact you had vertically integrated hydrological system, and it rained. The rain soaked in, groundwater infiltrated into the groundwater system, and that sometimes reached the surface, perhaps producing even oceans. And then at the end of the Noachian and into the Hesperian, this transitions to the cold and icy, cold and dry climate we see today. So what's the question, folks? Well, it turns out that climate models, which are really pretty sophisticated, this is something we all need to pay attention to, based on largely on the based on the faint young sun effect, okay, which is that the solar luminosity, which is about 70% of what it is today in the Noachian, suggests that it's not a vertically integrated hydrological system, that it's horizontally stratified. It's so cold that it's a global cryosphere like it is today on Mars. And any water that's in anywhere on the surface of Mars, in ice or other, particularly in the northern lowlands, that this would be sublimated and then snow out in the highlands. There's an adiabatic cooling effect. When the atmosphere is greater than a few tens to 100 millibars in atmospheric pressure, the altitude-dependent effect kicks in, and the adiabatic cooling effect kicks in. And that means that any water that's mobilized on the surface from seasonal changes or otherwise will, in fact, go to the cold traps and snow out, much like the north and south polar caps on Mars today. And the mean annual temperature is 225 K. It's crazy, because how do you, in fact, produce the valley networks and the open basin lakes and all the evidence for closed, for liquid water flowing across the surface? The climate modeling perspective is that it's a horizontally stratified hydrological system. It's a cold and icy with a sustained background climate. The ambient climate is 225 K, and that's what Mars should look like. It should look like an icy highlands, okay? Francois Forget, Robin Wordsworth, and others have explored and presented this model. It's a very robust model. We need to think about what that means. So what is the ambient Milwaukee climate? Is it warm and wet? geologists would say, well, hey, it's the geological evidence is really compelling. And they would say, hey, climate modelers, go back and, maybe twiddle the knobs a little bit and you'll get it right sooner or later, but it's just not going to be cold and icy at 225K. There's too much melting going on. So how do we reconcile these two very different interpretations, okay? And they are extremely different. So the warm and wet model, Luo et al., 5 kilometers global equivalent layer of water and huge oceans in the northern lowlands. The cold and icy model, maybe hundreds of meters of water GEL, and indeed that's likely to be mobilized and stabilized, actually stabilized in the southern uplands. So how do we understand this? You know, what is the ambient climate? Well, maybe we don't need continuous warm and wet conditions. For example, maybe it's cold and icy, but if you take a look at the frequency distribution of temperatures, remember we're dealing with mean annual temperature. Mean annual temperature is not peak seasonal temperature. It's not peak daytime temperature, okay? So Ashley Palumbo and work we did a couple of years ago basically plotted the frequency distribution of temperatures as a function of mean annual temperature 225K. And you can see here that temperatures here go out. In fact, they do go out. So at least one day a year in one location on the surface of Mars during this period, it can get higher than 273K. It's not going to do much at all. But if we were able to raise the temperature just maybe 18 to 20 degrees, 18 to 20 Kelvin, this would put us into a position where seasonal temperatures might actually create conditions in which you'd get significant melting of the ice sheets in the uplands, and maybe that's enough. Maybe it's an ambient cold and icy climate with peak seasonal and daytime temperatures that might actually create enough meltwater that we get what we see in the geological evidence. So that's where, in fact, that's where the Antarctic dry valleys come in. The current temperature is 253K. So the question is, what happens here if it's 253K? Do we ever get significant, that's mean annual temperature, do we ever get peak daytime and peak seasonal temperatures that might produce sufficient melting to explain what's going on in the Milwaukee? And so basically that's one of the most significant reasons we look at do field work in Antarctica. So this is a picture of one of our field areas, the one I just mentioned to you, which is Upper Wright Valley. And what you're looking at here is essentially a snow cap up here at the higher elevations. It also is sequestered in this alcove seasonally. And you can see it's also sequestered. You can see a channel coming down here, which is is like a valley network, if you will. And you can see there's some snow sequestered in this over the season. It snows. It's snow covered here in the southern winter. In the southern summer, it ablates away, and some of it melts. Okay, and you can see here. This is kind of, I won't. People freak out when I say swampy, but it's kind of wet and damp down here, and that indeed is the case. Okay, so what do we have here? Here's the mean annual temperature, 253K, and this is some of our data here going from essentially throughout the course of a year. We have all kinds of instrumentation associated with this, and we can get the year-long temperature. And you can see here that even though the MAT is 253K, the seasonal temperatures are approaching the melting point of water. And in fact, for some periods of time, you can see them heading up above in peak southern summer. They head up and actually exceeds 273K. That's when the beer doesn't freeze all day, okay? Typically, you can put it outside, and if it's in a can, and it better be in a can because the bottles will freeze, expand, and break. There are days when that'll work for a few hours a day. So that's what we're investigating here, okay? The basic hydrological system is horizontally stratified. This is what it looks like. Ice-cemented permafrost, dry permafrost, which is in diffusive equilibrium with the atmosphere, so it takes the ice out into the atmosphere. We have a glacier up here, and then we have potentially heating of this glacier during peak daytime temperatures, melting, flow of the water down here on top of the ice table. It's not penetrating in, it's flowing on top of the ice table, subliming when it gets down here and going back to the cold traps. So we have alcoves, channels, and fans, very similar. So for scale here, I think that's either me or Jay Dixon, I can't remember whom, and who would know, okay? Here for scale, this little red dot, let me go back, sorry. And you can see here, what we've done is, in this area, we've instrumented this area, the work of Jay Dixon, and get time-lapse photography for the whole area. So what we're going to look at here is a video shown here of the essentially several Antarctic days to show you what the peak daytime temperatures can do. So that's what we're looking at here. This is the time lapse, okay? This is a meter by meter grid here. And you can see as we go that, boy, during peak daytime temperatures, that meltwater, that ice in the upper regions there melts. It essentially comes down and flows out over the surface, and it's starting to do significant geomorphic work, okay? You can see basically here that it dries out. Look at this thermal wave as it's coming across. Then down it comes again, okay? And then it freezes, overnight freezing, and then that melts in the morning, okay? Overnight, of course, the lights don't go out because it's southern summer in Antarctica. And you can see there are cloudy days when we get wimpy flow, but then there are other days, in fact, when we get very significant flow. Okay, there you can see here, look at that erosion back. That's just one day, okay, of this meltwater. So what we conclude from this then is that, in fact, maybe this adiabatic cooling effect here and the precipitation of the snow and ice in the uplands and peak daytime and seasonal temperatures might actually be responsible. So if we have an equilibrium line altitude of +1 kilometer ELA, this is a perspective view looking down here. This might be what the ice looks like, and here's the ELA. And you get essentially peak daytime temperatures, which in fact are high and starting to melt the ice. The question is, does that potentially provide an explanation for the fluvial and lacustrine features we see in Antarctica? So here it is, the icy highlands model at +1 kilometer ELA, and we know here's an example of the Sierra Nevada in Spain. You can see the altitude-dependent climate effect here. Let's ask the question: what happens if we, in fact, start to top-down melt this? Well, it turns out here's the distribution of valley network shown in blue, open and closed basin lakes shown in red and green. And you can see basically that they have a very high correlation. I could show this in terms of a statistical plot as well, but trust me, it works. And you can see all the lakes are focused around the margin here. So, hey, maybe this is a solution. Maybe the ambient climate is cold and icy, but we just have peak seasonal or daytime temperatures that create the melting event. And that's kind of loud, but what that does is show you one peak daytime temperature melting event in Antarctica in our field area. There's a lot of water that comes off the top of those glaciers, even though it's completely permafrost and cold-based glacier that it's melting. So we've calculated, Jim Fastook and I, or Caleb Fastook and I did this actually, using Caleb's estimates, and we found that in fact open basin lake total volume is about 0.42 million cubic kilometers, and 1 year, 2,000 years of climate excursions of plus 18, 2,000 years, which is nothing, could in fact produce that amount of meltwater. So we think this is feasible. So the bottom line here is that here's a good example of something that's applied to the characteristics of big problems on Mars. What is the Milwaukee and ambient climate? And this fieldwork, among the contributions of many, many other people, has, I think, brought to question, could this actually be an ambient, cold and icy climate that has peak daytime, peak season, or maybe, generally warming, kind of like release of greenhouse gases temporarily, et cetera. So that's a good example of, I think, how fieldwork can really help to address, maybe not solve, but certainly make new insights into this type of situation. So let me just move on now, finishing up with the analogs that we've done, and talk about some general guidelines for application to off-planet exploration, ISS, Moon, and Mars, and then we'll move on to an Apollo lunar exploration example and some tasks ahead for Artemis for the Moon and Mars. So just a couple of, these aren't random thoughts, but just a couple of thoughts. One of the things that in all this exploration that is so important is science and engineering synergism. You cannot just get on the ship and just get in the the deep sea submersible and go to the bottom of the ocean. You have to learn how this works. You have to do a lot of homework here. You have to learn uh, everything you need to know about the ship. You have to learn everything you need to know about safety. You have to get to know the engineers, etc. Science and engineering synergism, working shoulder to shoulder in any of these complex exploration endeavors is critically important. And again, infrastructure. You saw from those examples, without significant infrastructure, you can't do anything. It's like, oh, I think I'll go to the moon, check this out. Nah, not going to work. And human robotic partnerships, you could see with the deep sea dives. Human and robotic partnerships. Boy, we're not just going with humans, we're going with a human robotic partnership. You need to always weigh those parameters. You need to build towards increased capabilities with time. This is really, I'll show you in a few minutes how it happened with Apollo. Absolutely fantastic. Working with the scientists and engineers together. And indeed, that's what's going to be going on with Artemis as well. Systems engineering and systems integration. You're not in this just by yourself here. You need to really think about things in a systems engineering way. You need to think your way to the destination and back and figure out how all that works. You need to work in systems integration. If you don't know what that means, look them up and Google them, and take a course in systems engineering if you have a chance. It's really critically important to the success of any endeavor. Another thing is that these things are really complex. Okay, Dave Scott always told me. He said, Jim, the problem with Apollo. He was the commander of the Apollo 15 mission. We'll come back to him in a few minutes. He said the problem with Apollo is we made it all look too easy. So everybody thinks going to Mars is a piece of cake. And it wasn't, and it isn't. Okay, those are really important words, and they're absolutely true. Apollo was really successful. There were some absolute bumps in the road. The Apollo 1 fire, Apollo 13, etc. But it was really complex and hard. Okay. Another thing to think about is LEO, low Earth orbit, and the ISS. For the last 30, 20, what has it been, 20 plus 25 years, I guess, we've been inhabiting the ISS with our international partners. And prior to that, we were in low Earth orbit with the shuttle, Mir, et cetera, capabilities that we had for exploring low Earth orbit. That's great, but that is like 50 years of, in fact, thinking about things in a different way. And I want to refer to Krikolev's law here, which I made up that name, but not Krikalev. Krikalev is a Soviet cosmonaut, and now Russian cosmonaut, of course. But he's one of the smartest people I've met, and just an incredibly interesting guy. And he wrote this great paper in Acta Astronautica, and I'll come back to you with a reference for that soon. But which he said, look, we're having a problem here. We're facing creeping determinism. What does he mean by that? He means that because we're not exploring something, you're not really getting out like you are on the moon and other things like that and exploring the surface. The problem is that we're transitioning from using human capability and creativity towards determinism. You wake up in the morning, you download the day's tasks from mission control, and you press on and you do it. Now, this is in no way a negative statement about any of the current astronaut, cosmonaut, et cetera, corps. They are just brilliant, they're hardworking, et cetera, but they just don't have the opportunity to really fully exercise. This was Krikolev's point. We have to be not prisoners of our determinism that we've developed over the last 50 years of low Earth orbit operations and 25 years of International Space Station. This is something to keep in mind. I'll come back to that. The last 2 points are the moon, situational awareness, and T cubed, okay? Situational awareness, the astronauts on the surface are always going to be more aware and better aware of what's going on the surface than we are in mission control. We need to fight fight the urge to actually use all the tools we have. Hey, maybe we can get them on the surface, give them an iPhone, and they can just text us what's going on. You know what I mean? And we tell them that'll really be great. We can get back and forth all the time. You don't want to do that. You want to leave them alone. That's what T3 is all about. In Apollo, our strategy was T3, train them, trust them, and turn them loose. We were there in mission control and in the science support room, not science dictating room, to help them when needed. And Oftentimes they did need it, and that was where it worked very well. We were not there to tell them what to do on a minute-to-minute basis. We need to fight that urge, okay? And of course, with a feed forward to Mars, the last one, there's no direct communication, 15-minute time delay. I remember watching the descent of the Viking lander to the surface, and we watched the descent profile, and we realized that 15 minutes before it was supposed to land, it was either a pile of metal on the surface or it had landed successfully. But we didn't know. And so what does that mean? It means T cubed is really important because you're going to train them, you better trust them, and you're going to turn them loose, and you can't talk to them, okay? Because you can't have real-time communications very effectively. And so this is something that comes back to the role of science support. We really need to think about that, okay? So those are some thoughts. They're each probably an hour discussion in itself. Let me go on now to the Apollo Lunar Exploration Program and show you an example of how one of these missions worked in particular. And a little background here is that there were, in fact, 11 missions in 4 years, 11 human Apollo missions, astronaut missions in 4 years. The first four, 7 through 10, were precursor missions in preparation, testing out different parts of the hardware, etc. And just let me remind you for fun, a slide that Dave Scott put together. He put this together in 2013. The onboard Apollo guidance computer, kind of important, okay, it was about 1 cubic foot with 2K of 16-bit RAM, 3,600 words of core rote memory. Whereas the Apple iPhone 5, okay, 2013 has a memory capacity of 64 bajillion words. So, imagine doing that. Imagine doing that, okay? So that's what the technology was like, but it got done. The other thing that's critically important here is that with each mission, the capability increase. The science and engineering synergism works so well that after Apollo 11, whose goal was to land safely, deploy experiments, and collect rocks and soils, okay, how are we going to improve upon that? Increase stay time, increase the number of EVAs, demonstrate pinpoint landing to increase access, provide equipment for transporting material and tools. Till we got to Apollo 15, which is shown in yellow here, enable orbital plane change to access high latitudes, increase the number of EVA periods to 3, and provide mobility to reach distant targets. Let's put a car in there, okay? All of this was a trend, and I'd be happy to come back sometime and talk about the history of the Apollo program with each step of the way here. But the key here is let's focus on Apollo 15, where we had all these new capabilities, okay? And it launched on July 26, 1971 to the Hadley Basin Rim, the Hadley Rill area, sinuous rill area, an incredibly important location here with multiple scientific objectives. And in fact, you can see here that it required a lunar orbital plane change. So all the other previous missions had been in equatorial orbit. This required the spacecraft to do a plane change, which meant that they had to basically that the orbit would precess around, and once the landing occurred, you had to find the orbiter. Okay, you had to find this command and service module, which was not trivial. Okay, so the second thing was that because of the landing site we chose, which you can see here in the Hadley Apennine region here, okay, these are the Apennine Mountains. This is the plains at Hadley, lunar volcanic plains. This is the Hadley sinuous rill. And basically, you had to land, because you wanted to be on this side so you could access all these things, between Mount Hadley at 14,000 feet high and Hadley Rill, 900 feet deep. This required a really steep descent path. So it required another change, okay? So, gee, can we do a steeper descent than we've ever done before? Dave Scott said, hey, yeah, let me give it a try. I'll go into the simulator. He flew a couple of those. He says, piece of cake, we'll do it. And that was a major thing. That's another part of the science and engineering synergism. We needed this. They accomplished it. There's Dave and Jim on the surface with a lunar roving vehicle. How the hell do you get that thing in this area? Trust me, really interesting. You should watch some of the deployments. It got there. Would it work? Well, we didn't really know, so we had to do contingency planning. It worked, okay? It was just amazing, okay? So there it is in all its glory. And you can see from, in fact, Dave sitting here anxiously, come on, Jim, take the picture, let's get in. We got work to do here on the plains of Hadley. These are the geological traverse maps here. And you can see they're kind of fuzzy, and that's because we landed in 20-meter resolution image data, okay? 20 meters. But the engineers had gotten enough confidence we could land on Mare surfaces They said, well, okay, 20 minutes. Are there any boulders? We don't know. Well, okay, we can navigate around those. Dave, Scott, and Jim Irwin, we can pilot around those, no problem. Think about it. So Apollo 15, one SEVA, I'll explain what that is in a second, 3 periods of EVA, 7 kilometers radius from the lunar module, total traverses 30 kilometers, okay, 30 kilometers for crying out loud, 77 kilograms of rocks and soils, okay? So this is really amazing. What's a SEVA? Well, because we didn't know what the surface looked like, Dave Scott had the idea, look, we'll touch down on the surface, we'll depressurize the lunar module, and then a key point here. We'll get in our spacesuits. We'll depressurize the lunar module. I'll open the top hatch, stand up on the ascent engine cover, and do a surface EVA. Okay, essentially trying to look out and see what the traverse might look like. We have traverse planned already. Okay, because we knew where the major objectives were. But could we see boulders? Were there boulders? Could we see boulders? And where are they? And how does that, for you people working on the contingency plans, how does that change our traverse plan? So that was brilliant because we had 20-meter resolution images. And so once they got down on the surface safely, we could kind of get an idea of where the rocks and boulders were. And by the way, there weren't very many, which would send us into I won't say tizzy, well, let's say a flurry of replanning and thinking about what we do in that case. So what did we find out? What did Jim Irwin and Dave Scott find when they got to the moon? And was it really significant science? There were huge accomplishments of goals and objectives as well as key discoveries. One of the things we wanted to find out were, could the Hadley-Apennine Mountains have excavated up deep crustal material and what did it look like? We wanted to get the coarsest grain of northosites we could find in these traverses to the base of the mountains. Dave Scott, from a few meters away, looked at this, saw plagioclase twinning, really reflecting in the sunlight, and said, Houston, I think we found what we came for. Because he knew from meters away that was an anorthosite. Gary Lofgren, one of the trainers at JSC, had spent hours with Dave and Jim showing them what the anorthosites look like, et cetera, and how to recognize them, et cetera. And he spotted it from meters away. Absolutely amazing, okay? And it was the right thing. This is 15415, the Genesis rock. Absolutely amazing. There were discoveries too. Dave Scott, you should go listen to the transcripts. Absolutely amazing. The excitement in Dave's, we've got glass, we've got green glass, like absolutely amazing. And it was green pyroclastic glass beads. Absolutely amazing. 40 some years later, Alberto Sol in our lab at Brown found water in these glass beads. I mean, it was really amazing, really amazing. This revolutionized our thinking. So we had both data from the goals and objectives as well as discoveries. We also tried to understand what was going on with the formation of sinuous rill, Hadley Rill, et cetera. The rock layering in the outcrops. This is a picture taken by the 500 millimeter lens, which was specially put on Apollo 15 mission to get high resolution data across the rill. And when we looked at these, of course, we found a lot about the rill, and we're still working on this. We just submitted an abstract to LPSC where we think we have finally a model for the formation of sinuous rills. It's actually very consistent with what Dave observed in these 500 millimeter lens images. So another example here of the beauty of the astronaut crew who are exploring the surface, by the way, I'll just do one quick rant here. I hate it when people say that the Apollo astronauts were scripted, and we're going to change that. You don't go into the field unless you have a exploration plan. Nobody does. I mean, unless you're on a vacation, okay? You have an exploration plan. You know where you want to go. You know what you want to do. That's why they had checklists and things like that. That was not a script. That was suggestions, okay? And basically remember, kinds of things we want to do in different kinds of environments. So that's exactly what they did. So these were not scripted. They were traverse plans. They were altered real time, mostly by what the astronauts said on the surface because of their situational awareness. Just one example is we also talked a lot about gases, gas and magmas, molten rock coming up. What's going on? What's creating these pyroclastic deposits? How does all that work? And Dave and I and many others talked about looking for rocks that had vesicles in them because they would tell us what was going on. So on the way back, I think at the end of EVA2, Dave is driving back to lunar module. It's at the end of EVA. The consumables are running out. Well, they aren't running out. They're low. You need to get back to the lunar module. Houston saying, press on, back to the lunar module, you know, and Dave's Roger that, we're on it, we're on our way back, etc. He spots this rock over here, and says, gee, you know, Houston, he really knows that's a rock he has to have. And so he says, Houston, I'm having trouble with my seatbelt. And oh my God, well, I'm going to get off and fix my seatbelt. Okay, yeah, definitely do that. So he gets off, collects this rock, okay, which is a beautiful vesicular basalt. Told us a lot about volatiles and how they're coming out of the magma, etc. Puts it in a bag, brings it back to, gets on the rover, cinches up his seatbelt, and heads back. Okay, Houston, we're good to go. Everything's okay. Okay, great. Get back. You know, monitor your consumables, etc. Um, you know, uh, I call that an unauthorized stop. Dave always corrects me and said, Jim, it's commander's prerogative, okay, which I love. And, you know, I think you want to think about what's going on here with this. When Dave got back from the moon, we sat down a couple of days after he got back over to his house, and he said, you know, he said, Jim, I had so much fun doing the geology on the moon that I didn't even know I had my spacesuit on. Now, I have to say, as much of a geologist as I like to think I am, I'd be kind of looking over to make sure the Earth was over my shoulder there somewhere. Dave didn't even know he had a spacesuit on. He described it as being in the zone. Like if you're in sports, you're up at bat in a baseball game, there's 100,000 people screaming and yelling. You don't even hear them because you're in the zone waiting for that pitch and putting it out of the park. That's what Dave was all about. That's what we need the astronauts to be like. Not cup checklist people, you know, not filling out something sent up by mission control, but in fact exploring. And that's a good example of what Dave did and other astronauts did too throughout the Apollo program. So here we are with the EVAs here. This is a perspective sketch really from the site, the 3 EVAs that were accomplished. And I just want to go over a couple of things here to talk about the first scientific expedition to the moon. So science and engineering synergism were critical. This led to increased capabilities during Apollo, increased daytime, lunar roving vehicle, up mass increase, flexibility, restructuring of the crew training goals and schedule, and we'll talk about that in a second. Essentially real-time modification during the traverses with whatever they discovered, etc. That was our job. High latitude, steep descent, 20-meter resolution data, new tools. We'll talk about those in a second too. We got on this mission the high resolution 500 millimeter lens as well, camera, as well as a rake to get smaller fragments, etc. Multiple, varied, and complex goals and objectives. Site selection and traverse planning. This is really critical, okay? All of this, the traverse planning, I spent a lot of my time when I was at NASA headquarters working with an engineer, Jack Sevier, to work on the traverses for the 15, 16, and 17 missions. We needed to think about contingency planning. We needed to be there, okay? And this is important. This is a topic we could talk about it with another seminar sometime, but the role of science support. The science support was the Apollo Lunar Field Geology experiment. It was actually an experiment, like a seismometer, et cetera, and that's the way it worked. So that was a really effective kind of way to go, okay? And we can talk about that at some other time, but supporting the surface operations is really important, and we need to do that in a way that leaves them to exercise their own situational awareness and their own intelligence, so we're not exercising creeping determinism, to quote Sergei Krikalev. So how do we train for all this? Well, we did lots of field work. We did simulations in mission control. I could go on for this for hours. It was like incredible. We had full up sims for mission control, et cetera, prior to the mission, et cetera, for the astronauts in the field, et cetera. And then we would do post-mission debriefing when they got back, and all this fed forward to the next mission. We just learned this from analysis of the samples. That means we know that. Let's go on to this next site, okay? All of that was going on throughout. And I want to just point out a couple of things here. This is a slide made up by Apollo 15 Commander Dave Scott, and it's complicated as hell, but follow the dot here, okay? Bouncing ball. So after Apollo 12, Apollo 15 crew was assigned, okay? Dave reviewed the training plan. He noted that there was a significant amount of time in developing and testing a toilet and microbiology. He axed that out, and with management approval, got geology training increased, okay? So this is the green here. These are the geology field trips. The LIM upgrade, okay? Lunar roving vehicle, scientific instrument module, and the command and service module. all these things went back and forth and increased the capabilities. Steep descent trajectory, which I just described. Dave did a lot of simulations on that. Piece of cake, okay? Landing, piece of cake, okay? Rendezvous simulations, direct ascent. I wouldn't talk about that, but that was a major thing as well. And then, of course, getting tools on board, the 500 millimeter lens, the rake, etc. That also occurred and was really critically important. You can see here the Hasselblad's lunar surface cameras, the difference between a 60 millimeter and a 500 millimeter. Here you can see Dave carrying this over to the edge of the rill to get that picture I just showed you. And in fact, this is a picture from the slopes of Mount Hadley. This is looking out towards the landing site, okay? If you look at a little closer, there is the lunar module with the 500 millimeter. There it is, and there it is. And if you don't think being 7 kilometers away from the lunar module is not being out there, this ought to convince you of that. So what's the legacy of all this, okay? The key, remember, is not just doing it, but what's the legacy? Well, critically, the legacy of Apollo 6 lander surface exploration mission, the last three, which were clear scientific expeditions of the Lewis and Clark quality, really gave us fundamental insight into the missing years of Earth history. So if we look at a clock as essentially recording history of the Earth and the Moon, essentially we only have the last half of Earth history, not very much from the first half at all, whereas the Moon provides us with insight into the formative years. And that's really, really, I mean, if you have one thing to say, that is really critically important. And it also, of course, is a cornerstone for understanding the other terrestrial planets. So we have a huge legacy, and we need to make sure that we have that for the future. So let's talk about, in closing here, essentially lessons for human, lunar, and planetary exploration. First of all, it's so easy to make science complicated, but when you try to tell engineers, when you try to tell your family and other people who are not scientists what science, it's just exploration of the unknown. Keep it simple because that's exactly what it is. Also, Apollo. It wasn't just about Apollo 11. It was the Apollo Lunar Exploration Program, okay? That's why 15, 16, 17 were literally scientific expeditions, okay? I can bore you to tears with a detail of that evolution sometime, but let's not do it now. If we look back at the Apollo Lunar Exploration Program, what's past is prologue. I love the Mark Twain quote, history doesn't repeat itself, but it rhymes, okay? So there's a lesson to be learned from this, okay? And again, the Apollo Lunar Exploration Program, International Space Station Transition, it's exploration to operations, and that's just the way it is. And that's why this Krikalev paper, 2010, Crew on the ISS, Creativity to Determinism, Astronautica 6670, send me an email if you can't find it and I'll send it to you. That's really important to read because this ought to be the roadmap for training crews in the way they should explore the Moon and Mars. And again, for Artemis program exploration, Krikalev's law, balance exploration and operations, really, really important. Okay, so I want to just finish here with a couple of points about some tasks ahead for Artemis for the Moon and Mars. So here's a list of things I'd like to see. I think we need to create a culture. Get that science and engineering. You need to be working shoulder to shoulder with the science and engineers. It's really important. This is not something that happens naturally. You've got to work on it. You need to engage and embed the scientific community in the process. That hasn't really been the case in low Earth orbit for a while, okay? It just hasn't been the case. It needs to be the case again. We need to build that, okay? Invest in learning each other's language. Trust me, engineers and scientists and operations people don't speak the same language. You have to invest time in learning each other's language. It's too easy to say, they don't understand. You got to learn. You got to teach. You got to learn. You got to work to get that science and engineering synergism. The other thing is systems engineering. You need to think your way to the Moon and back. This is critically important. I worry now that Artemis is, because there's no Artemis program, there's no Artemis program. There's no Artemis program director. How does that work? Okay. I worry that there's not sufficient systems engineering. We need to be integrating more. We need a lunar surface operations and exploration plan, not just, we'll get out and we'll pick up rocks. We need to think about astronaut training in the train them, trust them, and turn them loose scenario. And again, we need to think about human and robotic exploration as a partnership. We need to bring back lots of samples, okay? Again and again and again. And I'll just illustrate this by the fact that, if we're going to go to the South Circumpolar region, you're not in Kansas anymore, okay? You're much more like Apollo 16 than you are like any other sites. There are no benchmarks or landmarks except craters. If we're trying to understand the South Pole Aitken Basin, you're going to be looking for a needle in a haystack, folks. And we need to adjust crew training for this as well. This is really important. We also need to bring back samples, lots of samples, okay? This shows the essentially radius away that each of the Apollo missions accomplished. And the key thing here is traverse distance, okay? Um, Apollo, before Apollo 15, it was less than 5 kilometers, okay? And look at 15, 16, and 17, you're getting out to 35 kilometers. And look at the sample mass returned, okay? So here you get essentially, over 100 kilograms for Apollo 17. And they're all good, okay? And the thing you got to know about Artemis with the walkback constraint and with the up mass and return mass that are constrained by Orion, for Christ's sake, we're going to get probably less than we got on Apollo 11, okay? Certainly less than we got on the first missions. How can it be 50 years later we're constrained in our upmass for return lunar samples? There's a reason for that, and I'm happy to talk about that sometime, but we need to really work on that, okay? And I guess the last two things that are really, really important is engage youth and diversity. Sometime after I saw the movie Apollo 13 a long time ago, I ran into Jack Schmidt and I said, "Hey, Jack, what'd you think of that? Wasn't that essentially the way the best example? I've seen hundreds of space movies and they're all poopy, but that was really good." And he said, "Yeah, but there was just one thing wrong, Jim." And I said, "Oh, what was that?" All the actors in Mission Control were too old. I said, "Oh, don't you remember we were all less than 30? The average age was less than 30." I said, "Oh yeah, you're right. All the actors were too old. Who would believe a bunch of 20-somethings in Mission Control?" Well, that's what it was. So engage youth and engage diversity. Apollo happened 50 years ago. The gender distribution was predictably what it was 50 years ago. I'm sad to say, but it was. We now have over 50% of the population that did not take part in Apollo in a fundamental way. We need to change that. Think what we can do. Think what we did with Apollo. Think what we can do with twice the number of smart people thinking about it. Okay, and then of course Artemis, forward to the moon and Mars. Okay, the past is prologue. Forward to the moon and on to Mars. It's an exciting endeavor, and I hope these fieldwork and exploration analogs have been useful for charting that path. And I'll just close by saying that if you have any questions, etc., please do send me an email if there's anything explicit that I can't answer. So thank you, Jen. I hope that covers what you had in mind.
And that's
one,
fantastic. Oh,
one
go ahead.
There's some elephants in the room here with Artemis. If you want me to come back sometime to talk about these, I'd be happy to do that. But
Thank you for the offer. And on behalf of the community, thank you for the work that you have done to this point and continue to do, and for taking the time to put presentations like this together and to share this information with this community, because this information is critically important as we go forward to the moon with Artemis and also onto Mars. So thank you for providing this as a resource that we can maintain forever, and it will all be online and available. I think we have a couple of minutes for questions. If anyone has any questions for Jim, you can raise your hand in the participant window and or use the chat. I'll start with just a quick question, going back to the first half of the presentation for Mars, when you're talking about the peak seasonal temperatures, and you showed that nice map of Mars showing where we have liquid water features, basically. Has that been done in Antarctica to show, even if the mean annual temperature is lower, if you get enough peak seasonal temperature, you get those, basically hydrology features? Has that been mapped out? I should know this, but I don't.
Has it been mapped out?
Yeah, because
Yeah.
of the temperature gradients,
Yeah.
throughout the
So
dry
so
valley.
we've done a number of papers using the Mars climate models to show what that mostly Ashley Palumbo and myself and Robin Wordsworth and others to show what that effect would be and the amount of meltwater. So we have a series of papers, which I'd be happy to send a little summary of, which show that indeed with a cold and icy Mars, with peak seasonal temperatures in a climate model, you can in fact you actually get the meltwater you get the accumulation where the valley networks are, and you get the melting where the valley networks are as well. And then, of course, you can see from that plot that the open and closed basin lakes are just, they're just at the edge of the equilibrium line altitude, exactly where you would predict if it was top-down melting. Does that answer your question?
Yeah, yeah, and it's a similar case for Antarctica, right? In the dry valleys.
Yes.
Same story. Yeah.
Yeah, yeah,
Okay.
yeah,
Yeah.
we've documented that in Antarctica as well. Yes, definitely. Yeah. Uh,
Perfect. And before I go to Bernard's question, have you read the book Across the Airless Wilds by Earl Swift? Have you read
no,
that?
I have not.
Oh, it's fantastic. It's about the conception and design and build and test of the LRV, and it was fascinating. And also the proposal and selection process, which is eerily familiar, was yeah, that was a good read for
Oh,
me.
that's great. Yeah, there's a lot of really good books
Yeah.
um, that someday I'll get around to reading.
Well, you're in the books. You don't even have to read them. You wrote them,
Yeah,
so
that's okay.
you
No,
lived
but
them.
I think Ron Creel, who was in charge of the thermal design for the rover. It's like he can tell you some incredible stories about this too, because it was just amazing. Think about the development of that over just a course of a couple of years, and you can see from that, like okay, we're going to take a rake, we're going to take a 500 millimeter lens, we got to have them space qualified, we got to have a rover. A rover? What? A car? Huh? Well, there you go.
Make it happen. Um, just briefly, Bernard Foyne, thank you for joining from Europe, by the way, Bernard. How would the role of assistant robots, Moon Alexa or others, in future crew operations or remote support, how would you like that, or how would that work?
Yeah, I think sometimes you've seen. Hi, Bernard. Good to see you. Thanks for
Yep.
tuning in. Sometimes you see these kind of like field assistant kind of things where you got a rover running along the side, and that's not the way to go. If rovers are used for transport, that's one thing, no problem. But robotic rovers, they can interpolate. They should be going out before the astronauts get there, and maybe three or four of them going out in spoke-like directions, navigating and exploring and essentially scouting with remote sensing. Oh, look, here's the olivine in huge quantities. Okay, so replan that traverse to go over there. And then I think again, once you finish looking at a landing site with a human thing, you can go back with robots to essentially mop up. Whoa, well, we should try over here because it showed this, and here's a trend, and we can go back and look at it as well. One thing we did in Apollo was, if we'd had, I worked on Apollo 19 to 22, which none of you have ever heard of course. Um, but what we were going to do was to have a dual mode rover. You instrument the rover at the end of the mission, uh, and then it traverses for hundreds of kilometers across the surface to the next landing site to interpolate. So that's another use of rovers. So lots of really important uses, and that's the key. It's not about is it humans or is it robots? It's human robotic uh, synergism, basically. But one thing to remember is that before Neil Armstrong set foot on the moon, NASA had sent 21 robotic missions to the moon. 21, okay? Precursor missions, okay?
Good
Mhm.
point. Good point. And we are over the top of the hour, so I think maybe a good place to end is a point that Dean Epler made in the chat. So I'll just read it for everyone. In addition to the science engineering synergism is the need for a third element, the operations. And good engineering and good science planning doesn't get you there without integrating with the ops planning and execution.
And if I
That's
could have the last word, Dean is absolutely right. And it's too long to say science and engineering and operations synergism, but it should say that. It absolutely should say that. And the operations and people were the ones that actually enable us to work with the science and engineering synergism results. Okay, so that's why we landed at Apollo 17 because the landing ellipse did not fit in there. The operations people said, go back, scrub all your pads, come back. It's going to fit at the meeting we're having at 9 a.m. tomorrow morning. And it did. Okay. That's how we got there. So operations, Dean is absolutely right. Operations is critical.
well, Jim, thank you again very much for sharing this knowledge. And thank you again to Ricky Guest and to SSERVI for putting this online for everyone else to see. So everyone, hope you have a good rest of your day. And thank you very much for joining and hope you come to the next one as well.